The interpretability of deep reinforcement learning systems is crucial for understanding how they interact with their environment. Vector quantization methods, also known as codebook methods, have been employed to discretize a neural network's latent space, suggesting emergent interpretability. However, the authors investigate whether vector quantization truly provides interpretability in model-based reinforcement learning. Through experiments in the crafter environment, they demonstrate that the codes of vector quantization models are inconsistent, lack uniqueness, and have a limited impact on concept disentanglement, which are all necessary traits for interpretability. Deep neural networks have advanced reinforcement learning agents' performance, but these black box models lack insight into decision-making and learned transition models. Interpretability is essential in high-stakes domains requiring human trust, such as autonomous vehicles and infrastructure. It is also crucial for analyzing behavior and developing adaptations when trained agents make mistakes or experience novel environmental changes. Vector quantization has gained significant interest in neural networks, driven by the work of van den Oord et al. 2017, which showed that VQ latent space discretization in generative models improves performance. Although not claimed by van den Oord et al. 2017, subsequent works suggest that VQ enables greater semantic interpretability of neural models. The authors examine whether VQ within model-based reinforcement learning captures semantic information about entities in the environment. They use the Iris MBRL agent, which quantizes the latent vector encoding of the world state in models' transition dynamics using a transformer. GradCam is employed for qualitative and quantitative analysis to determine whether codes are consistent and represent semantically groundable entities, such as objects, across diverse inputs. The authors find that VQ lacks the necessary constraints to enforce that disentangled codes correspond to semantic entities, and codes are not consistent enough to be grounded to a semantic concept. The Iris transition model architecture employs vector quantization, VQ, to replace latent state vectors with the most similar codes from a codebook. VQ, a data compression technique, models a latent distribution as a discrete set of vectors or codes. A VQ function Q maps input vectors to the closest code in the codebook, minimizing the mean squared error, MSE, between the vectors. In model-based reinforcement learning, MBRL, Iris leverages VQ to represent grounded entities, utilizing the codebook as an intermediate layer between the encoder and decoder. While VQ methods have garnered interest for their emergent interpretability, with previous works demonstrating that VQ codes can capture consistent states and exhibit qualitative interpretability through latent traversals, the connection between latent disentanglement and latent semantics or interpretability remains unsubstantiated. Moreover, prior works rarely quantify the interpretability provided by VQ codes. The authors identify a research gap in studying VQ interpretability in MBRL and position their work as a bridge between mechanistic interpretability and black box approaches. By adopting a white box approach to interpreting codes, they aim to balance theoretical robustness with the ability to interpret complex networks without requiring a complete understanding of their internal structures. This approach is motivated by the need to move beyond saliency maps and towards a deeper understanding of neural network behavior. The paper evaluates the interpretability of a machine learning model, focusing on codebook-based models, specifically the Iris model with a 512 code codebook. GradCam is applied to code inputs to generate heat maps, indicating the importance of image regions for each code selection. The study aims to understand the semantic meaning of the codes by examining their consistency across agent observations and episodes. Results show that 90% of the heat maps contain all zero values, revealing that only a subset of codes are actively contributing to the model's decisions. Examples of heat maps and cropped images are presented to illustrate the focus of different codes. While some codes are consistently associated with specific objects or concepts, others do not exhibit clear patterns. The paper also aims to quantify code interpretability by comparing embeddings from the last hidden layer of a pre-trained ResNet 50 model. This research contributes to understanding how codebook-based models make decisions and how these decisions can be interpreted in terms of the input data. The authors present the results of their GradCam experiments, which measure code consistency using mean cosine similarity and TSNE plots. Table 2 displays example crops from codes, while Figure 2a shows the mean cosine similarity results, indicating a gradual increase with a spike for the best codes. The similarity is compared to a baseline of randomly sampled crops, demonstrating that only a handful of codes exhibit consistency. Figure 2b further examines the top 10 codes with high mean cosine similarity using TSNE, revealing limited clustering and, in some cases, multiple clusters, which obscures the semantic meaning of the codes. The discussion section highlights that the model learned a limited number of codes capturing entities like grass, water, and resources, but these codes lack a consistent semantic theme. The authors attribute this to the insufficient constraints in VQ to enforce semantic disentanglement of codes, allowing the model to reconstruct the entire image using a combination of codes without cleanly isolating entities. This suggests that characteristics of discretization are crucial for ensuring semantic associations, warranting further study in future work. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. Disentangled representations in machine learning have been extensively explored in various studies, with significant contributions from researchers such as Alexander Kozatsky et al. And Lucas Klein et al. Kozatsky's work demonstrated the potential of learning new skills by imagining visual affordances, while Klein's study improved the explainability of disentangled representations using multipath attribution mappings. These methodologies aim to separate the underlying factors of variation in the data, enabling more interpretable and controllable representations. Disentangled representations have been achieved through various approaches, including generative models, contrastive learning, and self-supervised learning. One key approach is to leverage inductive biases, such as spatial or temporal coherence, to guide the learning process. For instance, spatially disentangled representations can be learned by exploiting the inherent structure of images, whereas temporally disentangled representations can be obtained by modeling the dynamics of sequential data. Another crucial aspect is the evaluation of disentangled representations, which is often challenging due to the lack of ground truth labels. Researchers have proposed various metrics, such as modularity, separability, and informativeness, to assess the quality of disentangled representations. Despite the progress made, there are still limitations and open challenges in this field. For example, the scalability of disentangled representation learning to complex and high-dimensional data remains an issue. Moreover, the trade-off between disentanglement and reconstruction accuracy needs to be better understood. Future work directions include exploring new inductive biases, developing more effective evaluation metrics, and applying disentangled representations to real-world applications, such as computer vision, natural language processing, and robotics. The authors of the paper draw upon several key studies in the field of controllable text generation, reinforcement learning, and neural discrete representation learning. These studies provide a foundation for understanding concepts such as codebook features, sparse and discrete interpretability, and neural radiance field codebooks. The authors then delve into an analysis of code frequency within their dataset. By organizing codes by frequency of occurrence, they observe that the model does not heavily rely on any single code, with the most frequent code appearing in just over 1% of the dataset. However, there is a significant drop-off in frequency between the top 10 codes and the rest, leading the authors to examine heat maps and crops with 3 distinct frequencies. The top 2 codes occur significantly more frequently than the 10th and 11th codes, while the median codes appear at a much lower rate. The authors decide to focus on the higher frequency end of the distribution because they believe that even if low-frequency codes are consistent, they will not occur frequently enough to provide useful interpretability. They argue that in many observations, these low-frequency codes will not appear, making them less relevant for analysis. Finally, the authors present additional cropped images in Table 3, showcasing examples of consistent and inconsistent code crops. The top 3 examples demonstrate more consistent codes, focusing on specific features such as stone, grass, and water. These examples are drawn from a dataset of 477 images. The analysis focuses on the interpretability of codes in a machine learning model, specifically their consistency and CO occurrence. Figure 3 shows the occurrence percentage of each code in the dataset, revealing that only a few codes are consistently represented. Table 3 provides examples of consistent and inconsistent codes, with most codes appearing inconsistent when randomly sampling cropped images. The authors propose that the model may have learned combinations of codes to capture entities, which is investigated by analyzing CO occurrence rates of codes. This relates to the concept of superposition, where a latent feature space represented by a set of d-dimensional vectors versus may represent more features than they have the dimensional capacity. Figure 4 displays a heat map of the CO occurrence rates for the 10 most frequently co-occurring code pairs, highlighting complex relationships between these codes. This suggests the model uses groups of features to represent concepts or individual features to represent multiple concepts depending on the input, aligning with previous works on mechanistic interpretability and superposition. The CO occurrence rates of codes in a dataset are examined, with a focus on the top 10 most frequently co-occurring pairs. Notably, Figure 4 reveals that codes 344 and 424 exhibit the highest CO occurrence rate, approximately 18%. This phenomenon is further illustrated in Table 4, which presents examples of crops from observations where these codes co-occur, showcasing consistency in the captured information. However, the authors acknowledge limitations in their findings. Specifically, they note that high CO occurrence rates are largely confined to a single episode, and that only a small percentage of samples can be interpreted. These limitations lead the authors to argue that vector quantization alone may not provide the level of interpretability suggested by prior literature. Instead, they emphasize the need for extensive analysis of all codes and combinations to achieve meaningful insights. This implies that a more comprehensive approach is necessary to uncover the underlying structure of the data, rather than relying solely on vector quantization. By highlighting these limitations and the need for further analysis, the authors underscore the importance of rigorous methodology in achieving accurate and interpretable results.